Professor Shinya for giving me this opportunity to talk here and visit Seoul. Today I want to talk about our recent results on Navier-Stokes equation about the half-space problems. Actually, we are interested in some stationary waves and existence of stationary wave and its asymptotic stability, as well as we want to obtain a convergence rate. These results are obtained through joint researches with Professor Shuichi Kawashima and Dr. Toru Nakamura and Professor Peijin Su. Here is contents of my talk. At first, I want to talk about our result on out-of-hole problems. This result is obtained through joint work with Nakamura, Kawashima, and Peijin Su. So here we consider ideal prototype model for gas. So as we are thinking about the one-dimensional half space, so we study this problem over this half line. Then I want to mention about some related results. Then we show existence of stationary solution, and then we show asymptotic stability and convergence rate. Then I want to talk about some parts of outline of proofs, but time is truly limited. Maybe I will skip almost all parts of this. Then after that, I want to talk about our more recent result, which is obtained with joint work with Dr. Toru Nakamura. That is inflow problems. So here we consider outflow problem. Then we consider inflow problems. The main result for this problem is this. So I want to show existence of stationary solution and asymptotic stability of this. So for these problems, I think it is impossible to get a convergence rate. So anyway, let me move to more details. As you know, this is a system of equations which describes the motion of ideal polytropic compressible gas. So the first equation is conservation of mass, and second one is balance law of momentum. Third one is equation for energies. Here, x is a space variable. As we are thinking about this problem over half line, x is some positive value. T is positive time, and rho, u, theta is unknown functions we are now looking for. Rho stands for density of fluid. U stands for fluid velocity. Theta is absolute temperature. As we are thinking about the ideal prototype gas, pressure is always Boyle-Charles law. Here, pressure P is given by these explicit functions. Nu and kappa are some physical constants. Nu is viscosity coefficient. Kappa is called thermal conductivity. Here, C sub B is a specific feat at constant volume. Gamma is an adiabatic constant. So for this problem, we need to put initial and boundary conditions. So we want to write down initial data by rho sub naught, u sub naught, and theta sub naught. To avoid the vacuum, we assume that initially density is strictly positive. Also, we assume temperature is strictly positive initially. Then moreover, we assume that so these initial data converge to some constant value as spatial variable x tends to infinities. Here, rho sub plus and theta sub plus must be positive. So for this, we need to put boundary conditions. So we can consider three types of boundary conditions. First one is outflow, second one is inflow, third one is impermeable boundary conditions. So especially today, I want to consider about this outflow problem mainly. So outflow problem means that flow blows out from the boundaries. So boundary value of flow is negative. So first equation of Navier-Stokes equation is hyperbolic. Then characteristic speed of hyperbolic part is just this u. So this means since we put these boundary conditions around the boundary, this u is negative. So that means the characteristic speed of a hyperbolic part is negative. Characteristic speed is negative. So so we don't have to put the boundary condition on first equations. Oh, sorry. Here, second and third equations are parabolic equations. We need to put one boundary conditions we need two boundary conditions then. So these two boundary conditions are necessary and sufficient for well-posedness of these problems. So on the contrary, we can consider another case. That means fluid blows in from the boundaries. So that case is U sub B is a positive. For this case, characteristic speed is a positive, so we need one boundary condition for hyperbolic part. So we need three boundary conditions. The last one is the impermeable boundary condition. That means there's no flow on the boundary. So U sub B is equal to 0. So as you know, this problem is intensively studied by many researchers. So we want to consider outflow problem and inflow problem here. So for this problem, we want to consider these three problems. So first, we want to, I'd like to talk about the existence of stationary solutions. After that, asymptotic stability of them and the convergence rate. So property of stationary solution is truly influenced by Mach number at infinity. So it is given by this. Here, U sub plus is fluid velocity at infinity. C sub plus is the sound speed at infinities. So by straightforward computations, we can get the characteristics of corresponding Euler equations at infinite state. It is given by these three. For supersonic case, all of them become negative. Then for transonic case, 1 become 0. For subsonic case, 1 become positive. So this picture plays an important information for our analysis. So about these half space problems, we have several results obtained by mainly Japanese mathematicians. So first step for obtaining some convergence rate and asymptotic stability for viscous conservation laws over one-dimensional full space is started by Professor Nishihara, Kawashima, and Matsumura. I hope everyone knows this. Then, for isentropic model in half space is started by research of isentropic model in half space is started by Professor Akitaka Matsumura in 2001. He classified possible asymptotic profiles of these problems. Then, according to his result, that case is classified into more than 20 cases. So actually, he said some asymptotic state is a stationary wave, someone is rarefaction wave, someone is a superposition of rarefaction wave and stationary solution, and so on. So, detailed analysis on these problems started by Professor Kawashima and I and Professor Peijin Su. So in this paper, which we have shown that for outflow problems, there exists a stationary solution and it is stable. The convergence rate for this problem is obtained by us. So it is obtained by Nakamura and my former student Yuge and I. So this is a result of one-dimensional case. For multi-dimensional problems, Kage and Kawashima studied same problem. That means stability of one-dimensional planar waves embedded in a multidimensional half space. Then they show stability. Then this convergence rate is also obtained by us, Nakamura and I. So he studied this case for arbitrary n, but we get a convergence rate only for n equal to space dimension n equal 2 or 3. So ideal prototypic model is the study of ideal prototypic model must return to this celebrated paper obtained by Matsumura and Nishida. So today we want to consider ideal prototypic model over half line. So first we want to consider existence of stationary solutions. So I want to write a stationary solution to Navier-Stokes equation with over tilde here, like this. Then, since a stationary solution is independent of time variable t, it satisfies this system of ordinary differential equations. Here we prescribe same boundary condition as the evolutional equations. Then first, we integrate first equations from x to infinity. Then we have these relations. Here, then letting x equal to 0 in these equations, we have these relations. Here, rho sub plus is positive, and u sub plus is positive. Also, we are looking for a looking for a stationary solution whose density is positive. So, in out-of problem, u sub b is negative. So, this relation tells us that infinite state of u sub plus also must be negative. So, this is a necessary condition for existence of stationary solutions. Then we integrate, substituting the relation into here and here. Then integrate this equation and these equations. We have this as first order ordinary differential equations. Here we have already linearized the right hand side at the infinite state. So this J is a Jacobian matrix at infinite state. Tilde F and tilde G are nonlinear terms. So actually, by straightforward computations, we see these functions given explicitly by this. Here, tilde F and tilde G are both quadratic. So in this first order ODE, endpoint u sub plus and theta sub plus is equilibrium point. Then let me summarize what we should do. Our aim is this. We want to obtain the solution tilde u and tilde theta connecting u sub b, theta sub b, and u sub plus and theta sub plus. This is our first aim. So to do it, it is more easy to diagonalize our system of equations. Here, lambda sub 1 and lambda sub 2 are eigenvalues of Jacobian matrix J. Lambda r sub 1 and r sub 2 are corresponding eigenvectors, and this is an eigenmatrix. Then we can diagonalize our system of equations. So to do so, we employ new unknown functions here. Then substituting this, we have this diagonalized systems. So then this is the diagonal part. This is the quadratic part. We are thinking about this one. Then first, we want to consider supersonic case. That means flow at the infinite state is very fast. Then by straightforward computation, we see that Jacobian eigenvalues of Jacobian matrix J are negatives. So that means endpoint is asymptotically stable. So precisely, there exists a small neighborhood which is called a stable manifold. Then if distance u sub b and theta sub b is very small, then there exists a solution which converges to a zero. Moreover, this both are strictly negative. We have this estimate. That means our stationary solution converges to zero exponentially fast. Also, this delta, this amount, it depends on this delta. This is a case for supersonic case. So in this case, we call it our stationary wave is a non-degenerate. This is a more complicated case. It is called a transonic case. That means Mach number at infinity is just 1. Then for this case, eigenvalues of Jacobian matrix becomes one of eigenvalues becomes 0. Another one is negative. So that means we have one-dimensional stable manifold, and also we have one-dimensional center manifold. Then, dynamics of center manifold is given by this scalar equations. That means this z sub x satisfies these equations. Here, gamma is over 1, and nu and kappa are positive. So this coefficient is positive. Hence, we know that if our solution, our boundary condition located in this side, then we have a stationary solution which converges to 0. So if our boundary condition is this side, then there is no stationary solutions because this trajectory is go away from the boundaries, away from the zero. So in one word, we have this result. There exists a stationary solution if U sub B satisfies these relations. Moreover, we need to assume the strength of boundary data is sufficiently small. Then we have this estimates. So here, this part means our solution go to zero exponentially fast. So which means the direction of a stable manifold. So this part comes from a direction of center manifold. So anyway, we have this algebraic decay. So the last case is a subsonic case. This case, one characteristic speed becomes positive. So one trajectory go away from the origin. So this case is relatively easy. There is one stable manifold, another one is unstable manifold. So if our boundary data satisfies this relationship, that means our boundary data is located on this stable manifold. There exists stationary solution which converges to origin exponentially fast. So this is the result of existence of stationary solutions. Summarizing it, we have these theorems. Then we want to consider the asymptotic stability of stationary waves. Sorry, before it, let me talk about some local structure of invariant manifolds manifolds for the transonic case. Actually, stable manifold, shape of stable manifold and center manifold is truly depends on these two numbers. So here, C sub plus is a specific heat at constant pressure, and P sub r is Prandtl number. Then to make a more delicate analysis of center and stable manifold, we write these functions by this form. Then we want to decide that these coefficients, C sub 2, C sub 3, and S sub 2 and S sub 3. To do it, we differentiate both of equations and substitute to these two into original equations. Then we can get this C2 is given by this, this S2 given by this. Then we can write a more detailed picture of a center manifolds. So that means theta is given by this. Then this C2 is given by this. And if Prandtl number is equal to 0, so that means C2 equals 0, then C sub 3 is computed by this. So hence we have this, these figures. That means if Prandtl number is less than 2, center manifold has this kind of shape, and if equal to 0, this kind of shape. If Prandtl number is greater than 2, center manifold become this kind of shapes. Then by the same method, we can get a shape of stable manifolds as this. So anyway, in one word, we see that property of stationary solution is determined by a Prandtl number. Okay. So here is a main result of ours. So that means asymptotic stability of stationary solutions. So we can consider three types of conditions. First one is supersonic case, second one is transonic case, third one is subsonic case. So in each cases, we must assume these assumptions. Then we know there exists unique stationary solutions. Then we assume that some condition on initial data. We assume that initially our data is initially satisfies contained in this function space. This B means a Helder space. Then moreover, the difference between initial data and the stationary solution in H1 sub space is sufficiently small. We assume that. Then we can show that there exists a time global solution in this function space. Moreover, so our solution to evolutionary problem converges to stationary solution in supermap norm. as time tends to infinity. That's one of our main results today. B, Helder space. Helder. Sorry, Helder. Yes. So actually, so we get the estimate of norm in a Sobolev space. Then using it, we get a norm estimate of a norm of a Helder space. The reason we use the Helder space is that actually we want to consider classical solutions. That's the reason. So anyway, so in the formal computations, Helder space is not so important. Helder space, Sobolev space is more important. Then there is a result on a convergence rate towards the stationary solutions. To do it, we need to assume a decay rate of initial data, like this one. Then we assume these smallness. Then this is the supersonic case. So moreover, if initial data decays in the rate of this alpha, we can show this estimate. That means convergence rate is completely same as this alpha. Then this is a transonic case. For this case, we cannot get such a good decay rate. Actually, we must assume we have some upper bound of decay rate in T. This alpha must be less than 2 multiplied by 1 plus square root of 2. So actually, I don't know this upper bound is optimal or not. But we have some result about these upper bounds. For ideal polytropic model, we have shown this alpha, upper bound of alpha is this one. For barotropic model, Professor Kawashima and his student Ueda and Nakamura has proved that. Also, for barotropic model, we need to assume we have some upper bound of alpha. So that is completely the same as this one. So on the other hand, scalar viscous conservation laws for degenerate case and degeneracy exponent equal to 2. Then Ueda and Kawashima and Nakamura shown that. Also, they need some upper bound. It is the same as this. But more recently, Kawashima and Kurata shown that we can take this alpha between 1 to 5. So according to them, this 5 should be optimal. So anyway, I don't know this upper bound is optimal or not for our problem. So let me talk about outline of proofs. So to use the energy method, we first define a perturbation large phi. It is given by a difference of solution to evolution equation and the stationary solutions. Then we assume that initially this is very small and boundary strength is also very small. Then we get this type of H1 a priori estimate. Then from this we get we get a Helder estimate by Schauder theory for parabolic equations. Then we can construct the time global solutions. Then using this estimate again, we can show a stability of stationary solutions. To get a convergence rate, let me explain only for the supersonic case. Then we assume same one, and moreover, we need to assume this algebraic decay of initial data. Then we make a time and space weighted energy method in L2 framework. Then we can get this estimate, and we make some induction steps for this beta and xi. We can get this estimate. Excuse me, how long do I have?
You have 12 minutes.
12 minutes. 12, 1, 2.
1, 2.
Okay, thank you. Thank you. Okay, so maybe so let me talk about some parts of proof of asymptotic stabilities. So this case is easy, so I want to consider only a transonic case here. Then we have a system of equations for perturbations. Then boundary condition becomes 0, and the initial condition is given by this. Then to analyze it, first we employ, we define an energy form, E. It is given by this. Then, by straightforward computations, if perturbation is sufficiently small in L infinite, this E is equivalent to a square of perturbations. So, integrating the equation for this E, we have this estimate. But here is some higher order terms. To handle it, we need to compute more higher order terms. Sorry, this is the equation for E. Then we integrate this one. Sorry. Then, sorry. So here we need to handle these terms. So to handle it, we employ a Poincare type inequalities. So that is this one. Then substituting this into here, then using this property of decay of stationary solutions, we substitute this. Then we can get this one. Then taking this delta is sufficiently small, we get the desired inequalities. Then to handle higher order terms, we need to compute more higher order estimates. So actually, we compute these amounts. Then we have these estimates. So combining this estimate and basic estimate, and moreover, using this smallness, we have this H1 a priori estimate. So from this, we have a Helder estimate by using Schauder theory for parabolic equations. So that means we have a time global solutions. And moreover, these inequalities tell us that our perturbation tends to 0 as time tends to infinities. That's the outline of the proof of asymptotic stabilities. So to compute to get the decay estimate, we need more computations. So I want to skip some details for these problems. Yes. Then let me talk about our new result on inflow problems. So I have already talked about out-of-flow problems. So actually we can have a parallel result as out-of-flow problems even for these inflow problems. So this is system of equations. So we use the same notations for initial data, and for this problem we need 3 boundary conditions. Then existence of stationary we want to consider existence of stationary solutions. This is the same equation. It is time independent, and this is the boundary conditions. And actually, essentially same computations. We can get the same system of equations. But for this case, for supersonic case, 2 eigenvalues become positives. So there is no stationary solution which converges to 0. For transonic case, one characteristic speed is 0 and another one is positive. So that means if our boundary data is located on this center manifold, there exists a unique stationary solution which converges algebraically. Then for subsonic case, one is positive, another one is negative. So there is a one stable manifold. So if boundary data located on this stable manifold, then there exists a stationary solution which converges exponentially. Then by the so summarizing our observations, we have this existence of we have this theorem. That means there exist stationary solutions. For these cases, we assume these conditions. Then there exist unique stationary solutions. Moreover, we assume that initial data satisfies these conditions. Then we have time global solutions which converge to 0, in this L infinite norms. So actually, the step essentially the method to prove this stability theorem is same as the previous one I have told. So I want to skip these parts. Oops. Okay, so this is the end of my slide. So thank you very much.